In this series of videos I'm designing and developing a Z80 based computer system. As much as possible I'm trying to stick to the vintage way of designing things, so I'm using discrete logic gates for most of the circuitry. The only large scale integration device I want to use is the Z80 itself. So what I've done so far is develop a video output system, so I've been showing that in the last few videos. And earlier in the series I showed this, and this is of course the breadboard version of the CPU core. So we have the Z80 itself, and then tucked at the back we have a ROM. I had a RAM that I was using for some test purposes, but that's not actually connected to anything at the moment. And I then went and added the memory control system. Now there is quite a lot missing off this simply because of the limitations of trying to build on breadboards. If you go too far and it gets too big, it becomes unreliable, especially at high speed as we're using in this design. So the buffers etc. aren't here. I'm sort of leaving those out of this breadboard version, but I have included them in the PCB design for the prototype PCB. So we've got the Z80, we've got the clock, the reset circuit, and then the memory control, memory addressing, memory decoding, bank switching. That's all on these two breadboards here. As I say, there's quite a bit missing, but the basics are here. Now I haven't actually tried bank switching yet. I've allowed the Z80 to toggle the bank switch circuit, but the bank switch circuit's not connected to the decoder, so I don't yet know 100% if that's working. That's what we're going to be testing in this video. We've got the RAM itself, so again trying to stick with the vintage theme, I'm using DRAM, and all the control circuitry for the DRAM is also in the discrete logic. We've got some on the right here, and part of that is also of course in the memory control system. So I demonstrated this kind of working in a previous video and went through a very simple test program just to write values to a block of RAM and then read them back. But of course I need now to turn this into a PCB so that I can continue developing. I can't really add much more to this, otherwise it will just become unreliable. So I converted this into a PCB design, got some ordered and they've been delivered. There is a lot more on this than on the breadboards. We've got some buffering and various other things on here that I'll come to in future videos, and some of them in this video, but I have added all the things you would normally expect to see in this type of circuit. So I'll go and get this assembled, and we'll see if it actually works and does what it's supposed to. Okay, that took about an hour and a half to assemble. Went together quite nicely, everything fitted the way it should. And so what I've got here is the Z80, a ROM. This ROM has got the test 4 code in it that I've showed previously. I can't use the test 6 that we used in the previous video because that was toggling the bank switching, and of course without some code in the RAM, in the common RAM area, then it would crash if we try to switch banks. So I've gone back to the previous version of test code, and in theory if this works, this will just write a series of incremental values to a block of the RAM, read it back, and see if what it reads back is what it wrote. A couple of devices I've left out here. These are just buffering for the address bus. So this provides external address bus buffering, which I'm not using at the moment, as you can see, and this will be what we will use to connect to our ancillary circuits when we start developing them. But for now I can leave them out because they're not used internally on this board. And then all the rest of it is what we had before with a few additions. So it's the address decoding, the bank switching, the DRAM control, all that sort of thing. We've got the reset circuit. I didn't have a 10 megahertz crystal, or at least not one that will run in this configuration. I've got some on order, but for now I've just tacked in an 8 megahertz crystal, so it will run a bit slower than it should, and I will need to change that before we hook up the video system, which needs a fairly specific clock frequency, as I demonstrated in the previous video. So what I would normally do is insert the ICs incrementally and test each block of the system bit by bit, one part at a time. But because I'm making a video, I'm going to jump right to the end game. I've put all the devices in that I think we should need for this to work. It's a bit of a risk, but I have checked across the rails with a multimeter and I can't see any issues there. The only issues, of course, will be if I've got something wrong and we get contention on the buses, it could damage some parts. But I've had a very good look at the schematic and I don't think there'll be any issues, but we'll see if this actually does what it's supposed to. So as I say, I've got the previous test program in, and this will just write values to a block of RAM and read it back and see if it's correct. The reset circuit also selects memory bank 2, and memory bank 2 is the bank that the ROM is in, and we'll come back to that later in this video. But for now, I'll get this hooked up to the logic analyzer, make a few connections, so it will be minimal connections to it. All I'm going to connect is the power rails, and I'll need to just connect things such as the halt and the interrupt lines, otherwise it will just act in a bit of an odd manner. And we can then try and power it up. I'll connect it initially just to power, and we'll check the current draw to make sure that it's not drawing a huge amount of power, and if it is, I can of course turn it off fairly quickly. It shouldn't draw much more than 300 milliamps, so I've got the bench power supply current limit set to 350 milliamps, and that should in theory help to protect anything if there's an error. So I'll get this connected up and we'll go from there. I've got the board connected to the bench power supply. The power supply is set to 5 volts, and the connections I've made, I've got ground connected, of course, V plus connected to the 5 volts, but I've also got the interrupt, non-maskable interrupt, connected to the V plus as well, otherwise it's going to keep kicking off the interrupt when there's noise on the line. There's no pull-ups on this board to stop that from happening. And I've also got the bus request and the wait lines connected to the plus 5 volts for the same reason. Otherwise, if we get noise on those lines, they'll start causing the system to behave in a very flaky manner. So we'll try and power this up and see what happens. So what we're looking for is something that is a reasonable power draw. I actually got it set to 400 milliamps, looking at what the breadboard version was drawing, and with the additional parts it's going to be drawing somewhere between, I suspect, 300 and 400 milliamps, probably the low 300s, but if it spikes up and immediately goes to 400 milliamps, I will of course quickly turn it off. But we'll try and switch it on and see what happens. Okay, so I don't know if you can see that, it's drawing just on 300 milliamps, which is quite promising. It means, in theory at least, we're not getting anything catastrophic happening on the board, and the next thing we have to do is see if it's actually doing anything. What I'm going to do is try pressing the reset button and see if the current changes, and that will give us an indication as to whether it's doing anything at all. And it's dropped down to 281, back up to 2, so it is doing something. So what I'll do is I'll get this connected to the logic analyzer, and we'll start looking for any activity. And in particular, we're just really duplicating the testing we were doing with the breadboard version, and we're looking to see if this system can successfully write to RAM and read back the values it's trying to write. I've got the board connected to the logic analyzer. Unfortunately you can't see it anymore, it's buried underneath all these wires, but rest assured it is under there somewhere. And because this is a prototype board, I brought a lot of connections out to these connectors along the edge of the board. So we've got a connection up on the top right here to the memory address bus. We wouldn't normally have all these here, but as I say, it's a prototype board, and this makes it very easy and convenient to use this as part of a development project. And then below that, we don't have anything connected to at the moment. That's the buffered address bus. That's what we'll use to control our peripheral devices when we start to develop them. And then on the left, we've got all the control lines for the CPU, and at the top we've got the data lines for the CPU. So I've got one of the data lines connected to the scope, and that's just so we can see what's going on in sort of general terms, and it's a good idea to look at that. If we're getting contention on the data bus, it will show up. We'll get weird looking signals. What we're looking for here is a fairly clean appearance to the signals, and if we're getting what appears to be contention, again, I'll turn it off fairly quickly, but if everything looks good on the scope, it means that our timing's all correct, but we'll have to see how it appears when we power it up. I've got the control lines I mentioned earlier connected to V+, and I've got the other two channels on the scope connected to the CPU read and write lines. And because this test code that we've got in the ROM is going to start by writing to 256 memory locations, it will write an incremental value. We should see a block of writes, and so we'll see one of the channels giving us a block of pulses, and then we should see a block of reads. And in fact, the reads will be continuous because effectively we are reading RAM whenever we access the ROM. Sorry, reading memory whenever we access the ROM. So the read will be fairly continuous, but the write should be in blocks if everything is working. And then we'll have a look at the logic analyzer and see what it's doing in a bit more detail. So fingers crossed, let's get this powered up, keep an eye on the scope, and see what happens. If we just get a few pulses and it stops, then we know that it's kind of jumped off into space and something's wrong with the memory decoding or the addressing, or there's just a fault on the board. So power it up and see what happens. Okay, that's looking good. So the purple is of course the blocks of write, so that's where we're writing the 256 bytes to the RAM. The yellow trace is the read line, so that's where it's accessing either the ROM or the RAM, and along the bottom the blue line is just the data line that we happen to be monitoring. So we'll zoom in, have a look at the signals, see how they appear, do a single capture, and they're looking quite good. In fact, they're looking very good. So we're getting the write pulse, which is the purple pulse, nice clean sharp edges, no sign of contention. The data bus is looking extremely good, so that's we're getting different levels because there are different devices talking on to the data bus. Some are the memory chip, some are the ROM, some are the CPU itself, and they all give slightly different levels, but there's no sign of contention. Again, nice sharp edges and no little runt pulses showing that we might have contention somewhere, and so that's exactly what we wanted to see. Good, so that's looking promising so far. So another good sign is that it's continuing to run. You may recall with the test that we have in the ROM at the moment that if it detects an error, if it reads back a value that's incorrect from a memory location, then it will jump to a very tight error loop and we'll see all this stop apart from the ROM access. And because it's continuing to go around in loops, it's a good sign that it's reading back the correct value. Also, the fact these are at regular intervals means that it looks like the code is running as it should do, and we're not kind of jumping off into space and running to the end of memory address space. Okay, so we'll move the camera, have a look at the logic analyzer, and see if what we think is going on is actually working. So looking at the logic analyzer, I've got this set up in the same way we had it in the previous test. We're looking at all the control lines for the Z80. We're looking at the address lines and data lines from the Z80 as well. And also at the bottom we have the 8-bit address bus that's going to the DRAM. And what we'll do is a very similar test to what we had before. So we'll trigger the analyzer on an address of 9000 EE, and that's towards the end of the block of RAM that we're testing. The block of RAM is from 9000 hex up to 9000 FF. And we are also interested in the read part of the cycle. So if the analyzer triggers, it means we've successfully written incremental values to memory addresses in the DRAM from 9000 hex up to EF, and at this point we will have successfully read back the correct values from address 9000 up to EE. So we'll arm the analyzer and see what happens, and it's looping round and round, so it will keep going round. We don't need to restart it. And it has successfully triggered, which is a very good sign. So if we look at the analyzer, we can see that at address 9000 EE we are getting a data value of EE, which is exactly what it should be. And we'll trigger it again just to make sure it is going round, and it is. You can see it's going round and round. It's doing this very quickly, so that's a very good sign. It means that the system is working up to this point. So I'll just move the camera back down. So this is a good start. The board does at least appear to be able to access the DRAM. It means that the decoding is working to a certain extent. We appear to have reset into the correct bank, and that's what we need to look at next. So if you recall this diagram, this is our bank arrangement. This is our mapping for the overall system. I've selected to use 2 banks, and the ROM is in bank 2. Now the reason for doing this, of course, is if we put everything into a single bank, because the Z80 can only access up to 64K of RAM, we would lose the amount of RAM that the ROM occupies. And also because systems such as CPM need to access the very bottom of RAM, if we were to use something like this in a single bank, we wouldn't be able to run CPM or something similar. And this also gives us a lot more flexibility. And as I said, the system, when it resets, selects bank 2, and the ROM is at the bottom of that bank, so it starts at address 0 when the Z80 resets. It branches to address 0, so the program counter is loaded with a value of 0, and it starts fetching and executing instructions from that address. Now we can't just switch to the other bank. If we switch to bank 1 directly, then the system will crash because there's no code in this bank, and if, for example, the program counter was at for example address 20, if we then just switch banks, we'd end up at maybe bank 1 address 21, and then without there being any code there, because it's just got random data in that was created or was there when the system booted up, it will start fetching just random instructions, and it will obviously it's very unlikely it will do anything useful. So what we have to do to test the bank is start by creating a new test program, and the test program will now have to start to take on the elements that our final boot ROM will contain. So it's going to have to copy some code from the ROM up into our common RAM, and then it's going to have to branch to the code it's copied, and it can then switch banks. Because the code is in common RAM, it will be available irrespective of which bank we're in, and because it will effectively be in both of these because it's the same area, we can safely branch to it. And if our code is, for example, testing the memory as we did before, we can now test any part of the memory as long as we don't test the part that we've copied our test code to. So I hope that made sense. So what we are going to do is create a test program. It's going to copy a block of code from ROM up into common RAM. It's going to branch to that block of code, and the block of code will then test the RAM at the bottom of RAM. So in other words, it will test this bit of RAM down here, and the reason I'm using the bit of RAM down here is because if it conflicts with the ROM, then we'll be able to see that straight away, because of course the system can't write into the ROM. So I've actually already written this code. I'll just get the listing. So this is the code in question, and I've added a few things here that we're not really using at the moment, and because, as I said, this is now taking on the general structure that our boot ROM will have to take when we start developing it, because we will have to generate a BIOS and some boot ROM, etc. So the first thing it does is it jumps over a block of values here. Now these could be text, it could be vectors for interrupts, it could be anything, but this is generally what you want to do, is jump across some values, and we will need some values here for initialization. So it jumps to some initialization code. In this case it's very simple. This is normally where you would maybe read your floppy disk and configure the system. In our case, all it's going to do is copy some code into common RAM. So we're going to copy it up to a common RAM starting at address 9000 hex, and the code we're going to copy is this block here, and it probably looks familiar. It's exactly the same block that we've used for the memory testing before, except that it's now been relocated up to 9000 hex. It was running from 0 previously in the ROM, but now we're going to move it up to 9000 hex. Once we've copied this, and we're going to do that using the LDIR instruction, it's a very efficient way of moving a block of code. So a single instruction, in this case we're going to move 30 hex bytes, and it will move this entire block up to an address starting at 9000 hex. Once we've done that, we will branch to the first instruction of the code we've just copied. In this case it will be up here, and that the first instruction will actually switch banks. So this these two lines cause the bank switching circuit on our board to be toggled. In theory it did work when I tested these instructions on the breadboard version, but it wasn't then hooked up to the RAM and the memory decoding, so fingers crossed this will do what it's supposed to. And if it successfully switches banks, it's then going to start testing the RAM. This is the reason for testing the RAM starting at address 0, because if it hasn't switched banks and we were to test a block of code, or block of RAM rather, in the common RAM area, we wouldn't know it hasn't switched. But because we're testing RAM addresses starting at 0, they're the same address, albeit in a different bank, that the ROM occupies. So we will have to switch banks, and it will have to actually switch banks for this test to work. If the system doesn't switch banks for any reason, then most likely this will cause the system to crash. So again, fingers crossed it's going to work. The first thing I need to do is swap out the ROM. So I've got the new code in the ROM, of course. I'll swap the ROM, and we'll power it up and see what happens. So I'll power it off, I'll get the ROM swapped. So I've taken the old ROM out, I've got the new test ROM in there, and as I say, what it's going to do, it's going to start by copying the code from the ROM up into the common area of the DRAM. That will be very quick. We won't be able to see that initially on the scope. What it will then do is it will hand control to the code it's just copied, and that will start testing the RAM starting at address 0. And on the scope we should see something almost identical to what we had before. If we see nothing at all, or just a brief flurry of activity and then nothing, we know that something's wrong with the bank switching or the way it's copied the code. So I'll power this up. Okay, that's looking good. So we'll zoom in to make sure it looks fine. Okay, it looks as it should, and it's still running, so that's a good sign. So what we'll do now is we'll move the camera up, look at the logic analyzer, and see if we're capturing what we expect. So I need to change the triggering now because we're testing a different area of the RAM. So in this case we need to change the address to something within the first 256 bytes of the DRAM. So we'll change it and we'll set 00, and in this case we'll use, just for argument's sake, B0. And again we want the read part of the operation, and if this is working then when we trigger this it should actually capture some data. So we'll arm the analyzer and it seems to be working. We've captured a value at B0, which is what we set, and the value there is B0, which is what it should be. So remember, the test code is writing incremental values that match the current address, and then it's going back and testing them all. So there's no chance of it just carrying over on the data line the rogue value. It has plenty of time between the writes and the reads, and of course the data values and address lines will all change state quite a few times in between anyway. So that's looking quite promising, and also it's not branching off into space because it's responding fairly quickly. And what we'll do in fact is set up a trigger so it has to go around a number of times. So we'll set 1000, so it will now go around the loop 1000 times. It will write 256 bytes, it will read back and check 256 bytes, and it will do that 1000 times from the point at which I arm the analyzer before it triggers. So we'll see how long that takes. So I'll arm the analyzer now, and it's finished. So I didn't edit the video there, it took about 2 or 3 seconds, so we'll try that one more time. So okay, it's obviously running quite quickly. We'll run a bit faster than this once we get the 10 megahertz crystal in. Remember, it's only running with an 8 megahertz crystal at the moment, but even so it's running at a very respectable speed. It's able to access memory reliably and quickly. We're not getting any bottlenecks. I'm not using any wait states in the memory access. We don't need them because we're using 150 nanosecond memory. But I will be testing the board to see what the maximum speed is it will run at reliably, but first impressions are fairly good. Well, that was a lot less eventful than I was expecting it to be. The board seems to be working as it should do. The bank switching is working, the memory addressing is working, and we'll need to do more in-depth testing of course, and I'll be testing each block of RAM independently to make sure that the address decoding is doing exactly what it's supposed to, and that the memory boundaries are where they should be. But it's looking promising. We can switch banks, we can access DRAM right down to 0 in the first bank, we can access the ROM, we can access the common RAM, we can move data around, and it's doing it reliably. We're not getting any weird behavior or glitching or crashing. The current draw is now about 328 milliamps, and that's very respectable considering what we're running here, and it's a good indication that all the timing is what it should be. Nothing's getting hot, as I say, nothing's causing any issues, and it's not crashing and misbehaving. So what we'll do in the next video is start hooking this up to the video display system, and we can then start writing a bit more meaningful test code, start sending some data through to the display, and from that point on we can start designing the ancillary circuits and expanding the design.